So we need to prove the following. So let's start from the left hand side of a given equation. On the left hand side we have 2 times secant squared theta minus secant theta whole raised to the power of 4 minus 2 times cosecant squared theta plus cosecant theta raised to the power of 4. So this is our expression on the left hand side. Now if we want to prove that this is equals to the expression of the right hand side, that means we need each of the terms to be written either in terms of cotangent function or the tangent function first. So let's start with the identity. This is the most general identity, sine squared theta plus cosine squared theta, that's equals to 1. Now if we divide each terms with cosine squared theta, so our first term will then become sine squared theta over cosine squared theta, so that gives us tangent squared theta plus cosine squared theta over cosine squared theta, that will become 1. And on the right hand side, 1 divided by cosine squared theta, so that will become secant squared theta. So this is once and another identity which can be obtained from this standard identity. Then we're going to consider this particular identity, sine squared theta plus cosine squared theta equals to 1, and divide each of the terms with sine squared theta. So that means sine squared theta over sine squared theta is going to give us 1. Cosine squared theta over sine squared theta, so cosine over sine, that ratio is the cotangent function. So we'll have cotangent squared theta equals to 1 over sine squared theta, so that's simply cosecant squared theta. We'll be using these two properties. So our first one, we have 2 times secant squared theta. So in place of secant squared theta, we can replace it with 1 plus tangent squared theta minus. So in the second term, we have secant theta raised to the power of 4. But what we can do, we can rewrite it as secant squared whole squared. So secant squared will be tangent squared theta plus 1 whole squared minus 2 times. So here we have cosecant squared theta. So this will get replaced with 1 plus cotangent squared theta. And coming to the fourth term, we have cosecant theta raised to the power of 4. This can be also expressed as cosecant squared theta whole squared. So we can replace cosecant squared theta with 1 plus cotangent squared theta whole squared. So we will do that. So we have 1 plus cotangent squared theta whole squared. So this is going to give us, so we have 2 multiplied to 1 plus tangent squared theta. So we have 2 times 2 tangent squared theta minus, now we have tangent squared theta plus 1 whole squared. So when we expand it, we're going to get tangent theta raised to the power of 4 plus 2 times tangent squared theta plus 1. So we're expanding it by using the identity a plus b whole squared equals a squared plus 2ab plus b squared minus, so we have negative 2 multiplied to 1 plus cotangent squared theta. So we have negative 2 minus 2 times cotangent squared theta plus, we're going to expand 1 plus cotangent squared theta whole squared using a plus b whole squared. So we're going to get 1 plus 2 times cotangent squared theta plus cotangent theta whole raised to the power of 4, which is going to give us, we have 2 plus 2 times tangent squared theta minus tangent theta raised to the power of 4 minus 2 times tangent squared theta minus 1 minus 2 times cotangent squared theta plus 1 plus 2 times cotangent squared theta plus cotangent theta raised to the power of 4. So here we will see that this positive 2 and negative 2 cancels out. We have positive 2 times tangent squared theta and negative 2 times tangent squared theta cancelling out. Negative 2 cotangent squared theta and positive 2 cotangent squared theta goes away, 1, and this should be actually negative 1 because we're multiplying with a negative number. So this is also going to go away, and we are left with only cotangent theta raised to the power of 4 minus tangent of theta raised to the power of 4, which is the expression on the right hand side. Hence, we have successfully shown that this particular equation is true.